Okay, so let's get started. Looks like we have 5 YouTube viewers and 5 so in-person viewers. Yeah, I mean, this is a cool topic, so hopefully other people watch it later on. Anyway, we'll be talking about semantic parsing. Wow, you know, like this is actually the class I would love to teach if there were just 6 people in the class and not 100, whatever. Anyway, so semantic parsing is the task of given some sort of natural language sentence or whatever, a natural language utterance, we are trying to convert this utterance into some sort of formal meaning representation. And the purpose of this is that if this meaning representation can get executed by some like external agent, so perhaps it's a robot that you tell it to move its arm or something like that, then you can actually tell the robot or the agent or whatever to complete an instruction using natural language and then have it understand what that means. So this process, converting natural language into some sort of logical form, this is the process of semantic parsing. Okay, so as a simple example, you can consider mapping like a SQL query into SQL and then executing it over some database, right? So how many people live in Seattle? You could map that into something like select population from city data, where city is Seattle, right? So this is just a straightforward SQL query, but you know, SQL is quite complicated, so maybe you would want, well, not really, but some SQL queries can be complicated. You might want a way to express your SQL query in natural language so that anyone can, you know, query this database, not just people who know SQL. So you can see from this figure, right, there are basically 2 modules here. One is the semantic parser, which is doing essentially this translation task of natural language into logical form. Then there's this executor part, which is actually executing the natural language instruction. So the executor part is usually not dealt with when we're talking about this task of semantic parsing. We assume it's usually like a black box, or you know, like the robot is given to us, or this you know, database is given to us, and we know how to execute SQL queries over the database. We are concerned with the first part. How do we do this translation? So, I mean, it's not just QA that this is useful for. For example, instruction following is a task that people care a lot about, especially in the context of robots. You know, if you tell something, go to the 3rd junction and take a left, this is obviously understandable to humans. A human could be able to do this. To get it into instructions for this robot thing over here, it would have to be mapped into something like this, these like the sequence of primitive operations that the robot could then execute to accomplish the same goal. So one of the most challenging and interesting parts of this problem is that we often don't have direct supervision for the logical form. So like it's very hard to get a data set, like a large enough data set of go to the 3rd junction and take a left paired with the exact logical form that you would have to take to accomplish that instruction. So what you normally do get is the output of the query, right? So I could tell someone, how many people live in Seattle? Give me an answer to this question, right? And so I don't actually see the underlying SQL entry, the SQL query that is run on the database to get this query. I might just have the answer and know that it's somewhere in the database. So it's very easy to get examples of data like this. It's hard to get people to write like SQL queries that correspond to the question. So this makes the learning problem pretty interesting. And so before neural networks and all of this, there was a fairly large body of work on different methods to accomplish semantic parsing that were more grammar focused. So we used to have these CCG grammars in which for every word in a lexicon you would give it a specific type and tell the model, or in your grammar you would have rules to combine different types together. So for example, move here is a type of action. If you have move to, there's a specific rule to combine these two things. And eventually you're just parsing the sentence into a specific logical form like move to chair and so on, which can be executed by whatever it is that you're doing. So a lot of work went into learning the grammar and the lexicon to allow this composition to happen. But things have changed since then. Now, I think very few people are actively working on things like grammar-based semantic parsing. Mark Johnson, who worked a lot on this kind of stuff, called this the classic approach in 2016. So, you know, there are some issues with this kind of approach. Like if you're building a grammar, it might require manual engineering of the grammar, or you might have issues with the coverage of your grammar to like unseen situations and stuff like that. But yeah, it's very difficult to learn one of these grammars or engineer it properly such that it covers a lot of situations. So when sequence-to-sequence models came out, we had a new way of tackling this task and just formulating it as a translation task. So this very first paper assumes that you have the logical form as well as the ground truth question. So we already said this is not a realistic setting, but this was the first work in this regard, and we'll talk about more complicated methods where the logical form is not observed later on in the class. But if you assume that you have a question like what Microsoft jobs do not require a BSCS, and you have the logical form associated with this, which will give you the answer when executed over some database. So here you have some weird logical form that gives you this answer. I mean, we can use any of the techniques that we've already learned in this class to solve this problem, right? Nowadays, you might take a T5 model and fine-tune it to produce the logical form. This approach with supervised logical forms was already pretty close to the state-of-the-art with all these grammar-based approaches in 2016. Now, of course, we have much better models than in 2016. And this kind of thing, if we have enough supervised logical forms, very easy to repurpose any of the models that we've discussed. So what are some issues with treating this problem as a sequence-to-sequence problem? Can you think of any?
Maybe some words would really make sense in the output, like a logical form, including the subwords.
Yeah, so one interesting thing about the output space is that you have a very small vocabulary of like actions or like SQL operations or something, but you still need your vocabulary to be kind of expressive to handle the actual things that are filling the slots like Microsoft and so on. But eventually if your model is able to produce the right sequence of subwords, you can detokenize it and run it over with your executor to see if it gives you the right answer. You could also implement things like copy mechanisms such that your output can never produce anything that's either not in the input or not in its very tiny vocabulary of operations. So could be an issue, but probably not a serious one. Any other things?
What about the validity of the logical form? Is that something you can enforce with the sequence model?
Yeah, that's a good point. So this sequence-to-sequence model, right, we've talked about many ways of decoding from these models, right? Sampling-based or beam search or greedy search. None of those are guaranteed to output a valid logical form, right? And we know from, say, if you're applying greedy search, these models like to repeat themselves a lot, right? If they repeat, 2 parentheses in a row or 2 end parentheses or something, this is already an invalid logical form, right? So yeah, this is one of the big issues, and this will motivate some of the follow-up work in this regard to kind of try and make the decoder space constrained to only produce valid logical forms. So one of the data sets that is kind of popular with this semantic parsing task in NLP, at least, is wiki table questions. So this is a data set where you have a table, like an HTML table. It comes from Wikipedia, like this one about the Olympics and how many medals people won and so on. And there are questions that crowdsourced workers on Mechanical Turk wrote about these tables. And the answer to these questions is either a cell in the table or some aggregation of cells in the table. So here we have which athlete was from South Korea after 2010. And you would have to go down to the table and see that, oh, okay, well, I guess it's got to be Kim Yuna, right? And you don't get access to this. This is in some particular formal language, the logical form that you would evaluate to get the answer to this question. So in wiki table questions, you only have access to the question and the correct answer. That's all you have. So for this task, going back to the problem that you mentioned about invalid logical forms, if we use a traditional decoding algorithm, where at every time step you consider the distribution over the entire vocabulary and sample from that, you're going to get invalid logical forms. And with a task like this, you know that there are very heavy constraints on what can be produced at any given time step, right? If I produce argmax, then I shouldn't be allowed to produce argmax again, right? I should tell it first what the argmax is going to be over. And in this particular formal language, everything starts with parentheses. So at the first time step, you know that you have to produce a parentheses. There are no other options. Then there are some other operations, and only at certain time steps are you allowed to produce like some arbitrary column header or cell name or something like that. So at each time step, you can really cut down the vocabulary to only things that could be included in a valid logical form. So this idea of constrained decoding you can extend to many other problems, any sort of generation task where you have some constraints on what you're producing. Like if you know at this particular point you only want to produce an entity, then there's no reason to consider the whole vocabulary, right? You can just filter out your vocabulary to all the things you deem are entities and do the decoding like that. So it's a very simple technique and generally useful. So this is what we've been talking about, constrained decoding. The main point is to avoid invalid parses. Yeah, so there's kind of two different ways to accomplish this. The one that we just talked about is token level constrained decoding. So at every time step, we're going to add some constraints on the vocabulary. So the model is not allowed to sample the subset of tokens that we deem infeasible for the logical form at this point. There's also grammar-based decoding, which takes a different approach. So there are a bunch of papers on this. But yeah, this tree-based decoding is a little more interesting. So let's say we have, and this is a case, again, another use case of semantic parsing is like booking reservations, right? This is one of its most popular use cases. So if you have someone call, like an airline booking line and ask, give me a flight from Dallas leaving after 4 in the afternoon, this airline might have some automatic agent that tries to map what you said into something that can be executed over its database and actually assign you that flight. But to do so, we need to map this into some formal language that can be executed. So here we have another formal language where we see this logical form, give you something departure time greater than 1600 from Dallas and so on. So how do we produce this logical form? In the sequence to tree approach, this is a different way of doing the constrained decoding where you kind of proceed hierarchically. So you produce the first level of this logical form, and there's this filler slot, this n tag here. And every time you produce an n tag, you then do another level of decoding to fill in what goes into that tag. So you produce this thing, which is like the starting point of the logical form. And now you're trying to figure out what should go into the slot. So you do decoding again from just having this hidden state as input, and you produce and n, and so now there's 2 slots that need to be filled in. So you can fill in each one of those. The first one, you're trying to produce this greater than 1600 condition, and the second one here, you're trying to produce this departure time thing. Here you're going to do from Dallas, and so on. So at the end of the day, you've done this kind of hierarchical decoding where upper level is producing slots, the lower level is filling in those slots, potentially adding more slots, which are getting filled in by another level of decoding. So this is a kind of tree-based decoding that is useful in this regard because it lets you structure the query. If you know, I need to have 2 conditions here, or I need to have a condition and a column name or something like that, you can use this tree-based decoding to fill in the lower parts of the structure. So this is one approach, and the other one is a token level decoding. Yeah. So these things, generally, you induce the tree structure beforehand, so you already know exactly at what point this thing should produce slots and what those slots should be filled in with. So yeah, it's hard if you don't know the tree structure, then you have to induce a tree structure, or you have to consider many tree structures during the decoding, which is all hard. But this work just assumes that you have full supervision as to the tree structure also. Yeah. Okay, so the interesting part about semantic parsing is this weakly supervised case where you do not have full supervision. So we can't do things like this. We can't do things like this because we don't know at every token what the thing we're trying to produce is. We might only know the result of executing the ground truth logical form over the database. So the algorithms here are more interesting. So the fully supervised case, we all know how to do this. We have 2 sequences. We'll just train an encoder-decoder model to predict the semantic parse. But the weakly supervised case is more interesting. So in wiki table questions, for instance, we have the question, which is this X, which athlete was from South Korea after 2010? And we have the answer, which is a Z, Kim Yuna. What we don't have is the Y, the logical form. So no one has given that to us in this data set. We also have this W, which is the table, which we're using as context. So our task here is, given the question, given the context table, we want to find a logical form such that when we execute the logical form over W, it gives us our answer Z. So this is the weakly supervised task. You'll note that in the fully supervised setting, I don't even need an answer, right? Because if I have the logical form, I can just directly supervise my model to predict this. I don't need to do anything fancy. The interesting thing is, if I don't have this, now I have to rely on weak supervision in the form of just this answer. And the issue is that there is a huge amount of logical forms that could potentially evaluate to this answer, right? For Kim Yuna, I could ask, what athlete's name starts with a K? Or which athlete won 2 medals from 2010 to 2014, right? I could ask some questions that are completely different from this question, but those logical forms would evaluate to the same exact answer. So this problem of not having reliable supervision for the exact logical form that is paired with the question it makes this challenging. So there are 3 training methods that people generally use in this kind of setting. So we'll cover a couple of them. The first is maximal marginal likelihood. And here the idea is that for any given question and context and answer, I will essentially come up with a set of all possible logical forms that evaluate to this answer. And I'm basically just going to marginalize over these logical forms, and that will hopefully give me my final answer. So here, we're trying to optimize the probability of the answer Z, given the question and the context, if there is context. But we don't have the actual way of getting the answer, right? So we need a model that's producing these logical forms. And so if we are doing this, we're introducing this other latent concept of this logical form, and we have several different logical forms. So if we have a way of enumerating every possible logical form that evaluates to this given answer z, then we could actually do this summation completely, and we could get the answer, right? So our model could produce or maximize this probability. But as I mentioned, if you have a very complicated setup, if you even have a reasonably complex setup, this is intractable. It's very hard to enumerate all possible logical forms. And so you might have to do something more clever, like searching through the space to find logical forms that are particularly relevant to the question and not just arbitrary, but somehow evaluate to the answer. So this one is what we'll talk about in a little bit more detail, which are structured learning approaches. So essentially, these are ways of filtering out the space of logical forms to only consider logical forms that seem reasonable given the particular question. And so here, you generally have some sort of scoring function, like the model has a score that tells you at any given point, how relevant do you think this logical form is to the question? How likely is it that this logical form will end up executing to the answer? And there's, you could go all the way and use full reinforcement learning and have some other type of reward where it's like you get a reward of 1 if the logical form executes to the correct answer. You get a reward of 0 otherwise. But this is also very difficult to train because if you have this kind of setup where the model gets this binary reward only at the end of when it's completely produced the logical form, each logical form is made up of all of these different intermediate commands or arguments or so on. And you have to deal with the credit assignment problem of like, okay, if this logical form did not end up evaluating to the right answer, which part of the logical form that the model produced actually contributed to it going wrong, right? And with complex logical forms, this problem becomes very difficult, especially in these cases where we don't have that much data to even weakly supervised data. Like wiki table questions only has 15,000 or 20,000 training examples, so it's not very big, and the questions can be quite complex. So the structured learning approaches, essentially they use a bunch of heuristics to prune the logical form space. So one such heuristic could be, at any point, the logical form that I'm considering, do any of its components have string overlap with the question? Or if I am able to execute the partial logical form, so let's say I'm considering like a SQL query. So like going back to this example, let's say my SQL query was like select athlete where nation equals South Korea or something. So if I'm producing this logical form step by step, I might get to a point where I have select athlete, which is already a valid SQL query. And I can execute that over my table, and I can see, okay, does the result of select athlete intersect with the correct answer? If so, this is a strong signal that this is a good logical form, right? On the other hand, if I've produced select Olympics or select medals, and I execute this over the table, and there is no intersection with the answer, I already know at this point that this is not going to be the logical form that ends up evaluating to the answer, right? So if I have a scoring function in my model that's telling me at every single step what is the potential that this logical form has of being the answer, if I get some intermediate reward or signal, like if I produce select medals and this has no chance of ever being the answer, I can already supervise that scoring function to downweight the score of this logical form. So next time I see this, hopefully I won't produce that, and I'll instead produce something starting with select athlete, right? So many of these problems, you can kind of design these clever intermediate rewards to supervise your scoring function. And so one common approach in the structured setup is you kind of do a beam search or something like that, where your scoring function is learned by the model, and it's telling you, like, how likely is it that this particular decision will get me closer to the answer? And you can train it like this. And then there's a second step when, after you've kind of trained your scoring function, you can use it to get a logical form that ideally has some overlap with the answer. So maybe after some training, I'm able to produce select athlete from this question. Of course, it's not the right answer, right? But it has some intersection with the correct answer. And so one of the techniques that people use is, well, I don't care that it's not exactly right. I'm just going to use this logical form to supervise my final model. So given this question, I might train a sequence-to-sequence model to produce select athlete. Even though this is not the right logical form, the hope is eventually my scoring function will get good enough that the logical forms that I produce by decoding based on the scoring function have enough intersection with the answer that the model can actually learn a good semantic parser. And the supervision here is noisy. It comes from what the model is inducing from this kind of search process. So the difference between these kinds of structured learning methods and full-blown reinforcement learning is, in reinforcement learning, I could use, like arbitrary rewards. So I could use this binary reward, for example. You typically train using policy gradient approaches. This is not, I think, at least in these kinds of problems, not as successful as using a more heuristic-based approaches, but it generally depends on the constraints of your problem. So when you're doing this approximation of the space of logical forms, there are two ways to do this. One is what I just described, where you're training this scoring function. So the model has a score for partial logical forms, and that is guiding the search process and the way in which you constrain the logical forms that you consider. The other approach is just have some heuristic or some approach that is going to do this pruning of the search space before even you train the model. So of course this is more efficient. You only have to do it once and your set of candidates is static, but it's very limited, right? You might not be able to prune a lot of the logical forms if you only use some simple heuristics. And so the online search is definitely what people in this space have focused more of their effort on. Okay, so just stepping back a little bit, we have a sequence-to-sequence backbone which is producing these logical forms. And what we've discussed here is just how are we getting the supervision for the sequence-to-sequence model. If we have a data set with annotated logical forms, it's trivial. If we don't, then we probably need some way of searching through the space of all logical forms, picking ones that seem promising, and then using those as supervision to our sequence-to-sequence model. So then, of course, we talked about these constrained decoding approaches, right? What actions are valid to take? What can the model output at any time step? Add constraints so that you don't produce invalid programs. And you need a way to execute these programs so that you are able to get feedback on whether or not the thing that your model produced is actually evaluating to the right answer or not. Okay, well, going pretty fast here. I guess that's probably good news for many of you. Let's see if there are any YouTube questions. All right, I guess not. All right, any questions? The slides? Mm-hmm. Yeah, so I think in a previous semester, I had a homework where I had people implement this constraint decoding. It's generally done rule-based. Like if you know that you've just, for example, produced select, right? Then you know that the only possible things that could follow this are column headers, say, or something like that. And so everything else in your vocabulary should be invalid here. So similarly, you can write a bunch of rules that depend on the previous output or the previous two outputs or something like that. If you need to match parentheses, right, that might be another thing to consider. But yeah, generally you keep some sort of lookup of what has been produced in the past, and depending on that, you should have constraints on the next time step. For the constraints? I'm not actually sure what people generally just write this as, yeah. So I don't know. I mean, you probably could do something better, but generally these kinds of languages are not like it. There is a data set that has just SQL queries as output. I think there's a data set called Spider. Actually, maybe I'll look that up because the logical forms in it are quite interesting. Okay, that's not one. Yeah. Let's see if we can find some examples. Oh, it does? Oh, yeah, yeah, cool. Yeah, so here, I'll zoom in. So this is a case where the logical forms are in SQL. What is the number of cars with more than 4 cylinders? This is fairly straightforward. But then you have queries that involve joins, right, which become more complicated. So here you have to join this concert and stadium table together. Here you have multiple joins, and here you like this is pretty complicated, right? What is the average life expectancy in the countries where English is not the official language? So it's cool that so many people have worked on this. I actually haven't seen this paper since it was released. But okay, what are the metrics here? Exact set match without values. Oh, execution with values. Okay, so I guess this means they get it right if their logical form executes to the right answer, probably, which is cool. So, and this one, okay, I'm not sure what this is, but yeah, it looks like there have been a lot of submissions this year even. So people are doing better and better on this task. We see one approach that's using Electra somehow, one with BERT on this. Yeah, I imagine this is some sort of sequenced SQL pre-trained model or something. But anyway, so in a case like this, it's probably quite difficult to write. Yeah, go ahead. That's true, but okay, maybe we should check. Yeah, because it's not really explained in the execution with, okay, execution accuracy. Okay, so I think that second table, which had all the other, it had like 50 or so systems, was doing this component matching thing, which is directly on the SQL statement. The other one was doing execution accuracy. So yeah. Yeah, I'm not actually sure. I guess you could check out this paper to learn more, but in any case, this is a very difficult data set. It only contains 10K Q questions, and I think it does give you the logical forms, but yeah, it's very difficult. So you can see, you use this as an example of something that's super hard. Okay, so let's go back to what we were doing. Right, any other, yeah.
What happens with the train logic constraint? Like at every time that we have to validate your entire
So your objective doesn't really change if you're doing constrained decoding, right?
do you apply this software only on the validators at every time?
I mean, I think there's multiple approaches. The easiest one is only to do constrained decoding at inference time, which I think is what many people do. And during training, you just hope that the model doesn't assign probability to, so the model can learn these kinds of patterns itself. On the other hand, if you have implemented these constraints, then you could also do a mask loss in the decoder during training. So I'm not really sure what the preferred approach is. So you, at any time step, you have only some subset of the vocabulary that consists of valid things to predict for the next time step. So you could run your softmax over the subset rather than the full vocabulary.
Question about the maximum marginal likelihood function. What exactly does that mean? Like, what are you maximizing over? Exactly.
The probability of the answer given the correct answer given the question and the context. Yeah. Yeah.
So in that case, you need the executor to be at every time.
Yes. Yeah. I mean, in every case that we discussed where you don't have the supervised logical form, you need to be using the executor to get feedback about what the model has produced. And you can imagine how slow this can be at times, yes.
This definitely can't be trained using neural networks, right? Because I don't see how this is effective.
Well, what is the executor?
Yeah, when you're using it.
Yeah, that's it. Okay, so the question is, I forgot to repeat the questions. If you're doing training where the executor is involved at any point, this is non-differentiable. Like, of course, you can't backprop through the executor to change its behavior. On the other hand, the approaches that we discussed, like the structured learning approaches, for example, they use the executor only to learn a scoring function for different components of the logical form that it's producing. At the end of the day, you get a logical form as weak supervision through some search process. And so this, you might have learned through the executor, maybe you use some heuristics or whatever. But both approaches treat this as a sequence-to-sequence problem at the end of the day. So either you have a supervised logical form from your data set, or you have a model-produced reference logical form, which you get through the search. And you can train your sequence-to-sequence model to produce this noisy logical form, and the executor is not involved in that process. So that's basically how it works. Yeah. So the question is there a way to basically tell the model that there's some noise in the logical form and it should know that somehow? I don't think that's generally how people do things. It's kind of unclear how you would set that up to have the model recognize there's some uncertainty there. If you have this kind of process and every time the model sees a question, it's being asked to produce a new logical form that you found with a better search, maybe your model got better at scoring the logical forms, then it kind of already bakes in some uncertainty because the model is being asked to produce different logical forms at different iterations for the same question. So at some point you would hope that you get good enough logical forms that it kind of converges. Okay, confused about why do we need constraint decoding? Wouldn't the language model condition on the sequence so far and have the soft constraints implemented implicitly? Yes, this is definitely true, and you would hope your language model learns these constraints. However, during the process of sampling, if you're using sampling or any sort of decoding strategy, there is some chance that the language model could produce things that violate these constraints, especially if you don't have that much training data and the model isn't able to learn the constraints fully. So having the constraint decoding is an easy thing to do at inference and kind of guarantees that you have valid logical forms. So that's why it's implemented. Okay. So one of the projects that I worked on in the past is a variant of the structured learning approach for semantic parsing. So can talk about that. The general idea is that you have something like wiki table questions, but you have conversational, you have like multiple questions about the same table, not just one question. So here, given this question, given this table about the women's water polo World Cup, we have, some countries, some medals that they've won, and you might have a series of questions. So maybe someone's trying to learn some general and specific information about this competition. Which nations competed in the women's water polo World Cup? Of course, this is easily answerable by just select nations, right? We'll give you the answer to this question. But in the multi-question context, you can have follow-up questions that refer to the answer of the previous question. So this is kind of interesting. Here, you could ask, of these nations, which ones took home at least one gold medal? And so this now has narrowed the context that the question is referring to, right? I'm no longer concerned with all of the cells in this table, just the cells that were selected for the previous question. And of these, which were ranked in the top 2 positions and so on. So it's very similar to wiki table questions. We can actually kind of ignore the conversational part for the rest of the slides. But we collect a data set which is similar to wiki table questions in that you have just the question and the answer and no logical form. So we have this weakly supervised problem here. Okay, so let's say we're given this question about the previous table. Which nations won at least exactly one gold medal? So if we look at this table, the answer is Hungary. It won one gold medal. But let's take a look at this process by which we come up with a logical form to supervise our model. So our ground truth might look something like select nation where the gold column is equal to 1, right? This is what we want to produce. So when we're doing our search process, we start out at some start state, and then conditioned on the question, we have some sort of module which tells us the score of any action that we can take at this particular time step. So here, our actions are not just like select, but also select plus a column. So any sort of select column combination is considered a valid action given the start state. And so we have this pi function here, which given the current state that we're at and any action that we are considering taking will give us a score. So we're trying to learn this pi function. And so when we're doing a search, we're searching guided by the scores that this pi function is giving us, right? So maybe when I'm searching, I come across these 2 paths, select nation and select rank, which are both highly scored. So I'm going to expand both of these, and this is similar to a beam search. We might actually just do beam search using the scores from pi as the way in which we're pruning different paths and so on. So previously, we saw beam search where the scores are the probabilities that the language model is giving us. Here, the scores are coming from a different function. So let's say I expand this path. So given state 2 now, where I've already produced select rank, I'm going to score the actions, and maybe I said that conditioning on gold is the next best action given this current state. And then maybe I'll add another thing, like equals 1 to fulfill the condition. And then finally, I have a complete logical form. I will evaluate it on the table, and I'll get an answer 4 of course, 4 does not match Hungary, so this path here is not usable for training my sequence-to-sequence model, right? However, if I go up to the top path, I have multiple options that I can choose from. So maybe I condition on gold, which is the correct thing, but also I gave a high score to conditioning on rank here, although that's not exactly what we want. And then from each state, I could, for example, do equals 1. So this top path is exactly what I want the model to produce. But this middle path, select nation where rank equals 4, is what we call a spurious logical form because it evaluates to the exact answer, Hungary, that we have in our data set. However, it does not match the semantics of the question, right? This is the logical form for a completely different question that just happens to also be Hungary. So it's very common to find multiple spurious logical forms when you're doing this search. And the model doesn't know here, like this path is worse than this path, right? The model thinks, oh, well, both of these are great. Let me just pick one and train my model to produce it. So this is one of the biggest challenges with these kinds of setups. The other challenge that I mentioned before is that we could do the search and we might never find a logical form that evaluates to Hungary, right? So then what do? Our scoring function clearly is not good at coming up with this logical form for this question. So one thing we could do is evaluate the intermediate logical forms, like select nation. Well, it's not correct, but it evaluates to something that has overlap with the correct answer. So maybe we can use this as partial supervision. Okay, so finally, when you do this search and you find a path that either has some intersection with the ground truth answer or is exactly correct, then you're going to maximize the score of each of the intermediate decisions that contributed to that path. You're going to minimize the score of all of these incorrect paths that did not evaluate to that answer. And basically, you're just going to train your model to predict the correct path. So this path or this path, whichever one, becomes used as supervision. So because you don't have the ground truth logical form, you're going to search for one and then train your model to produce it. That's basically the intuition here. So right, that you can see here the end-to-end training algorithm. We are approximating the reference semantic parse logical form because we don't have access to it. And the value function is trained to favor that parse, so that pi function here. Okay, wow, so I guess I'm completely done. One other question you might have is, how do you implement these kinds of modules, right? Like what does this pi function look like? And it can be anything, right? All you need is something that takes a state and a candidate action in as input and produces a score. So here you see for this, I think this is a select module. You have the question as a representation. You have the nation candidate column. You pass it through some model that is producing a single score, which is what you're going to use to decide what thing to produce. Yes? No, sorry. This is just one input to this. So at this point here, if I'm considering select nation, I'm going to put nation in as input to the value function. Yes? This is not a reinforcement learning. I mean, it's very similar in many aspects, but this is a structured learning approach. Yeah, this is one example of it. So here, the rewards are coming from these kinds of heuristics that we've made up, does this logical form have any overlap with the correct answer when we execute it, and so on. So it's not like the pure case where does this logical form evaluate to the correct answer, yes or no? That's very harsh, and we found that this kind of intermediate reward is necessary to get this thing to work. That said, this wasn't, so we proposed this algorithm, but I think a couple years later, someone just made like a transformer that did nothing special. I think it just took the question and the table as input and then had the model predict for every cell in the table, is this the answer or not, or something like that. So there was no logical form component. If your goal is just to answer the question, it's very simple to just say, all right, for every cell or collection of cells, is this the answer to the question? And this did way better than this approach. So, you know, I think semantic parsing is pretty cool. The machine learning algorithms are nice, but it's hard to beat some of these simple, dumb approaches. You know, it's not that dumb, right? That just means that we now have models that give us more powerful representations of things like cells and tables and questions, and we're able to train them on limited data to do some of this very complex reasoning, right? The fact that a transformer model without access to any formal language can produce these answers means that it's kind of imitating that process somehow with its weights, which is really interesting. Of course, this isn't always possible, right? So if you had a really huge database, then using some sort of model to score every possible entry or combination of entries in the database is still not going to be feasible. And you know, having some intermediate logical form representation makes a lot of sense in this regard. But yeah, there's this tension here. Yes. So I will pass this through my executor and get a result from the table, right? Yeah, so if I do select nation, I'm going to get these 5 things as output, and I know that Hungary is the correct answer. So I can devise some simple metric, like what is maybe like 1 out of the 5 things that I produced with select nation was correct. And so maybe this is a good path to consider in the future, right? So. Uh-huh. Sorry, can you say that again? Yeah, exactly. Yeah, I mean, so at some point you can't decide, or the model doesn't know, right? So if I have 2 competing logical forms, like maybe select nation and then what is it that you said? I don't know, like select the 4th row or something, and they give you. Yeah, sure. So you get, you know, like 2 different logical forms that have approximately the same reward. Yeah, I mean, you would hope that the model is using the question text as well to do some filtering of these kinds of things. But at some point, you're just giving it like some approximate positive boost to anything that has overlap with the answer, even if it's undesirable. And this is always going to happen because you just don't have any supervision at all for the logical form, right? So the approximate rewards here are going to be very noisy. Yeah. Yeah, so you use that partial supervision also during the search to terminate some of the paths. Like this path here would never have been expanded past this just because it has no overlap and there's zero possibility that it can ever overlap with the answer in this data set at least. Yeah, so that's another thing that's important is that when you're doing these kinds of things, the search space can blow up tremendously, and any sort of thing that helps you prune the search space is extremely valuable. So this is another thing that should be considered if you're trying to do RL on this kind of, all possible trajectories is just way too many things, and some intelligent pruning is necessary. At least it was then. I'm sure it's still needed now. All right, yes. Well, it is not producing, the transformer models don't produce logical forms. They just, given the question, their goal is to answer the question. That's the goal of all of these things, right? But one hypothesis is that it's good if you go through a logical form because you know how to execute all these things on the table. That should be helpful. On the other hand, the existence of papers like that is kind of counter to the intuition here. Yeah. Oh, so the question is about the data construction. Remember that there is no SQL query in the data set. The data set just consists of question, table, and answer. Yeah. Yes.
Did you say you did anything to like evaluate stories paths versus the desired path?
It's very hard to evaluate like which paths are spurious. Like the only way is to manually inspect, right? But we didn't, like we saw those during development, but didn't do any. I think there's a follow-up, sorry, there's another paper, I think it's by Percy Liang's group, maybe in 2018 or 2019, that takes an alternate approach where they do the search for the logical form using dynamic programming, going from the answer, starting from the answer and going backwards. So this is at least guaranteed to give you a logical form that evaluates to the answer. But even still, that's difficult. Yes.
Having a logical form would help in the zero shot because I mean you don't have to necessarily come up with the answer then for unseen entities or questions in general. You just come up with the logical form based on what the numbers are.
Yeah, so the question is, if you have a logical form, maybe your system is more usable in zero-shot situations compared to like this transformer case. It's a little unclear because you can easily pre-train your transformer encoder to be aware of many different possible types of tables or entities or so on. And if at the end of the day your semantic parser isn't able to handle queries that have out of distribution like words or question types or so on, then you'll run into the same issue, right? So it's kind of hard to make that statement.
So I guess in terms of content for the slots, for example, so if your question types remain constant for what the answered slots can contain corresponds to the zero shot setting.
It's a little unclear because like it's not obvious to me that the transformer approach is worse on this. If you give it a table with or query with entities that it's never seen before during training, it probably will be able to generalize. I mean, in these kinds of data sets, the tables at test and training time are completely disjoint. So the model is seeing new tables at test time and new questions. So it has to be able to generalize to some extent. Okay, well, that's it. And if you guys have any suggestions for topics for the remainder of the semester, I think we have like 3-ish, something like that, lectures left. Let me know. One of the lectures, probably on Monday, will be on the ethics of these huge scale language models. There are actually now even classes at other universities that are being taught on ethics of language models, and we'll try and get to some of the salient parts of those courses in one lecture on Monday. But then, yeah, any other suggestions, just drop them in the anonymous form, and we can think about doing them for the rest of the semester. All right, so see you on Monday.